So, we've talked a little bit before about when an object gets dropped, its speed increases, and so then the height above the ground is going to decrease faster and faster because it's gaining more and more velocity or speed as it falls. So, this is more of our basic equation for finding that value. And like it says here, h sub 0 is my object's initial height. Where does it start? And this h here is where does it end? Now sometimes it may say it ends at the ground. Well, that'd be 0. But other times it may have a specific spot that it ends and we have to watch for that. So, for instance, we've got Niagara Falls in New York's 167 feet high. How long does it take for water to fall from the top to the bottom of the falls? Okay, so from the top to the bottom. So the top would be my initial height, which is 167 feet high. This negative 16t squared is never going to change unless you're given a time value to work with. And that'll happen occasionally. But then when it says fall to the bottom, that just means my end value is going to be 0. Now, could I try solving this with the calculator and just using a root? Sure you could. Is that always going to be the easiest way? Not necessarily. So again, we'll get you a couple of options here on how you could go about trying to deal with this, but I'm going to try doing these graphically. So if I'm going to do it graphically, I'm just going to replace this t with x. So I'd have negative 16x squared plus 167. And then I'll show you how we can just do it algebraically too. Because again, some of you will like it one way over the other. Now here's the one thing you're going to have fun with though. When I go to graph it, you're like, whoa, can't even see all of this. But here's what I can see. When I'm doing these, my x-intercepts, or my zeros, are going to, are going to be my solution. That's going to tell me the time that it's going to take for that water to fall down. Well, one thing I notice right away, because I see here are my two zeros. Well, here, that's a negative number. I can't have negative seconds that it's going to take, so this one doesn't make sense. I don't even need to find it. This one, though, I do need to find. So there's a couple of things that I can do. I could either try to guesstimate again. Maybe I get lucky, and if I go to the table, it looks like it's around 3. I notice one thing, though. You notice here, when it goes from 3, it's a positive number, and 4, it's a negative. So this value is somewhere between 3 and 4. Now, I need to be a little more exact than that. So what I'm going to do is I'm going to do my second trace. I'm going to bring my calculate menu up, and I'm looking for zeros. Okay, I'm looking for x-intercepts. So I'm going to get my 0 clocked in here. And you're like, okay, oh, this is where we're going to trap that point in. Yep. I don't see, though, where the cursor guy is. Well, at this point, I got a couple of options. One of them would be to just start hitting the right or left buttons until he shows up. Okay, that would work. My other option would be, I notice when it comes up, it says y is already up at 167. So here's my other option, and I'll do this sometimes. I'll go to my window and I'll say, okay, if y is already up at 167, let's say I max out at 200 and see if I can actually see this then. That's a little bit easier to work with. Now I can actually see the entire parabola and make this a little bit easier when I go to find my 0. So once I change my window, I can go back to my second trace, which is how to get to my zeros, my mins, and my maxes. So it's the same table, that I use for all of those. I go down to my 0. Okay, now I even see my cursor guy. So again, I want to get down here closer to where the actual value is. Now you're like, now it's looking like I can't really see this as much. Okay, here's what I'll tell you on that. Notice I can see the y value still. It's at 4. If I go over again, it goes into the negatives. As long as I'm above and below the axis, that works. So if I'm here, Okay, I'm above my point when I'm trying to trap it, so that's okay. I'll hit enter. When I hit right a couple of times, when my y becomes negative, now all of a sudden, when I'm working with this one, if I know the parabola is working like this and my first point was above it, and now that y value is negative and it's below, I know I'm going to trap that point in. So it's some things you can do so you're not kind of crippled by having to deal with the window as much. And if I just hit enter twice, I'll get my 0 value. So this x value, this 3.23, is the amount of seconds it would take for that water to fall from the top down to the bottom. Now, if you are more algebraically inclined, if you're like, yeah, I'd rather just do the algebra when it's possible rather than having to mess with all this stuff in the calculator, that's okay. Because if I were going to go algebraically with this, I'd just say, okay, let's get t squared and these guys away from each other and solve for t. So I could subtract the 167 if I wanted to go that way. And then divide both sides by negative 16. And take the square root. Now let's see if I get the same thing if I do it that way. So if I take the square root of 167 over 16, okay, I get the same thing. Now the thing I'd have to remember is you're like, but it's plus minus because it's squared. But remember, we're talking about seconds. It's not going to be negative seconds. So I kind of ignore the negative and just use the positive. So again, the graph gets me there using a 0, or I can do it algebraically if it's a simple enough format for us to use. Same thing's going to happen on the next one. The only difference is going to be now we're dropping from a height of 213. So the only difference would be it's going to be plus 213 instead. And again, I don't mind whichever method you want to use to find it. There will be some that you have to do on the calculator though, so we're going to have to get used to some of the buttons with this sooner or later anyway. So when I get this set, let me check out the graph again. Okay, I can almost see it. But again, I notice the negative isn't going to do me any good. This is the one that I want. So if I do my 0, again, I don't see you. Where are you? There you are. Now, if some of you are like, I really do want to see the point, though, so I can see the above and below, okay, let's mess with this a little bit. Maybe my y value needs to be negative 20 so I can see a little more. So I can move the axes wherever I want to. If you want to make it even more towards the middle, hey, let's make it a little more towards the middle so I can see more. Because then when I go to find my 0, my intercept, now I can see it and I'm like, okay, that's about where it is. And like we said before, a couple clicks to the left gets me my left bound. Get back to my center. A couple clicks to the right gets me my right bound. And it'll tell me that it's going to take about a little more time, a little over 3.5 seconds to get there. But again, I could do it algebraically the same way I did this first one if I wanted to. When it's just a drop function like this, I absolutely can keep it simple. But of course, there's not always just going to be you're dropping something and that's the end. There can be some twists to things. And if anytime during this something screwy is going on with your calculator, you're like, wait a minute, what did you just do again? Stop me, because sometimes with you guys I think you're on a roll and I just can't keep rolling with you. So if we need to slow up a little, we can do that. Okay, a little more complexity. Stuntman working on a movie is going to fall out of a window 100 feet above the ground. For his safety, an air cushion 26 feet wide by 30 feet long by 9 feet high is positioned on the ground below the window. How many seconds will the stuntman fall before hitting the cushion? Okay, we know where he's starting. He's starting 100 feet above the ground. So plus 100. And like we set up above, the negative 16t squared will stay the same unless we're told the time, and we're not. But here's where this one's different. What value do I want to use for where he ends up as far as height goes? 9. We hope he doesn't end up at 0, because if he ends up at 0, he's splatting into the ground and is in big trouble. So those are the little type things I have to watch for. So now if I'm going to do it algebraically, I could, if I wanted to do that, I could subtract the 100 over. I could divide by my negative 16, which would turn those positive, and then take my square root. And again, that'll work on any of these drop problems that we were working with. So I always like to show you any option that we may have. So it's about 2.38 seconds. And again, the nice thing about doing these and then doing them graphically is you know if you're getting the right answer because, well, we already solved it. So if I was going to do this on here, what I would want to do is I would take my 9 and I'd bring it over to the t squared side. So if I was going to put this in my calculator, I would need to subtract the 9 over here because my calculator doesn't like it with that equals sign in the middle. So what I would do then is I'd get the equals 0 equation, put this part in, graph it, and then basically I would look for that 0 again, the one that's positive, the one that's over here. And again, left bound in this case just means I'm above the x-axis. I'll hit enter once, get back to about where it is, a couple extra clicks to be below, and there's that 2.38 again. So both ways work. Again, it's kind of a personal preference with that. But it kind of lets us see just how fast some of these things end up working. But then again, we may be able to take a little extra step with this. Because now we even get a second question with this one. A movie camera is operating at a speed of 254 frames per second records the fall. How many frames of film show the stuntman falling? Okay, so we're going 254 frames per second times the amount of time, 2.38 seconds, that our guy was falling. Oh, shoot. The seconds cancel, telling us how many frames it's going to be, and then we just multiply them together. So not everything's going to be some real complex form. So it looks like it's about 605 if we were to round up. We can't have half a frame. So it lets us take it a step further once we get that initial information. Now again, the formula up at the top, the negative 16t squared plus h of o, works when I just drop something. When I put a little more force behind it at the beginning, like I would if I launch or throw something, we get an extra term that gets put into the middle called v sub o, which stands for its initial velocity. Because if I really try to gun one to somebody, that's going to have a lot more speed at the start than if I just happen to drop it. So when you're looking at the comparison between these, between dropped and thrown, the difference is that initial velocity term that's going to be in the middle. This is going to make it a little more complicated for us to try and do it algebraically, where now we're going to probably have to depend on the calculator a little bit more. So our height model not only applies to launched or thrown, but to dropped as well. I could still use this formula even for the problems up above that we were doing, because my initial velocity if all I did was drop something, would just be 0 meters per second or 0 feet per second. I'd just plug a 0 in there literally. I don't know why I'd want to do that because it's just going to disappear anyway. But technically I could. I could use this expression for every single one that we ever do. But again, why would we? Because we want to make more work of it. Nah, probably not. So with this in mind, we're going to do a little flipping back and forth here with this. If I flip it over, I go, okay. So we've got the formula up here at the top again, so we don't have to do too much flipping. And just again, just as reminders, this guy's my initial velocity. That's my starting height. And this guy is where I end up. And again, the t squared we're probably not going to do a whole lot again with because we're trying to find the time again. So we got a baton twirler tossing their baton into the air. They leave the twirler's hand 6 feet above the ground. There's my h sub o. And has an initial velocity of 45 feet per second. Okay, so there's my v sub o. So it's going to be plus 45t. The twirler catches the baton when it falls back to a height of 5 feet. There's my h. And as usual, nothing happens with negative 16t squared. For how long is the baton in the air? So again, when we're doing these, we're attempting to find the zeros or the x values that would make this work. Now, I would not attempt wishing upon anybody in this section trying to factor this and get all the terms to one side. I could use the quadratic formula, even though we haven't talked about that yet. Some of you probably had some dealings with that. That would work. But the calculator is actually going to make this a little easier. I need to get my equation set equal to 0, though, because that's the only way I can put it in the calculator. So I'm going to subtract the 5 over. And that's the expression I'm going to plug into the calculator to try and figure out how long this is going to take. So I'm like, okay, back to y equals we go. We're going to type this guy in there. So negative 16. We're going to use x instead of t. And we're going to type this quadratic in, knowing we're getting a parabola that's opening downward because of my negative a value. So let's see if this fits. Okay, I can see that. Now you may be like, yeah, that's kind of starting to zone out here a little bit again. Okay, so if when I initially did my graph, maybe I want to start moving it back a little bit more. Maybe 200 seems too big now. Maybe now it seems more sensible to make that 50, and maybe I can put my negative y back to here. Let's see if this works. Okay. That makes it a little more clear. It still looks like it's a little bit large even, because I can tell by this big thick line that I have here. So some of you may be like, maybe we can get back to normal. Well, let's try it. And some of this is just going to be kind of seeing where everything's at. Yeah, I can see it there. That works. So once I get it in a spot I'm comfortable with, I notice this looks like the 0 I'm looking for. So again, second and trace, go to my 0. There's my cursor guy, but I want him over here. So I'm going to start right arrowing until I see him show back up. There he is. And again, left bound just means above the x-axis, and we're above there. So we'll go ahead and hit enter to lock that one in. One more right click gets me below the axis, and again, as long as I'm trapping that 0 in, which I'm doing, I can hit enter. I can go back up here, hit enter for my guess, and that 0 that I get at 2.83 would be how long in seconds that's going to take for that baton from when I throw it up to when it comes back down, hopefully into my hand and not going all the way to the ground. But that's the same process we're going to use on all of these. The only thing that we're going to have to think about is, well, where am I plugging the numbers in and how does this calculate out? So the same thing happens as we continue to go on. It's like, okay, me and my friend are playing tennis. My friend lobs the ball into the air, hits it when it's 3 feet above the court. 3 feet above the court, they waited an awfully long time. With an initial velocity of 40 feet per second. You back up and prepare to hit an overhead smash to win the point. Write an equation giving the height of the lobbed tennis ball is a function of time. Now that sounds really complicated. All that means is put it in this, because when it says as a function of time, it just means t is going to be my variable on this side. Now since we don't know some things yet, we'll start with the h. The negative 16t squared, okay, that's still not changing. But we do know the other information. We know our initial velocity. So that'll be 40t, and if you want to use x, you can. And it initially is hit 3 feet above the ground. So that would be my initial equation, writing this as a function of time. So at what time does the ball meet its maximum height above the court? Okay. Well, here's what I've got to work with. So let's type this in, and for our first time today, we're going to find something other than a 0. So we'll clear that out. Get our negative 16x squared plus 40x plus 3. Get my graph up. Again, I see the 0 that looks like it's going to make sense. It's right about in here. Now, but do I want to find the 0 this time? Is it asking me when the ball hits the court? No. Maximum height. We want the max on this one. You're like, but I can't see it. Okay. We know how to fix that. Let's say, let's try putting our max up to 50. Okay, that's better. Now I can see it. So when I go to the same trace, second trace that I did before, instead of going to 0, I'm going to go down to maximum. So now, my idea is to trap this maximum point in. So anywhere here on the left where my cursor guy is, I can hit enter. Then I make sure I find a point over here on the right of my vertex up here. Hit enter. Get back towards the middle there. And I find out my maximum. Now again, you're going to get multiple values here. We got to know what to do with each of them. Is at 1.25. We're here. And 28. Well, now what do each of those mean? Well, at what time, the x value is my time. So after about 1.25 seconds, the ball's going to meet its maximum height, or reach it. What is the maximum height? How high did it go? Like the y-axis goes up and down. At its maximum height, it's going to be at 28 feet. So I can get both of those bits of information from finding my maximum. Not only the time, but also what's going to go on with the actual height. So let's keep going with this. If you plan to hit the smash when the ball falls to a height of 8 feet above the court, how long do you have to prepare for the shot? Okay, so now, looking at my initial expression, it's going to start here. I'm going to wait till it gets back to 8, so I'd replace the h with my 8. And just like before, for me to be able to put it in the calculator, it needs to be 0 equals. I can't have stuff on both sides. So I'm going to minus the 8 over. And once I've done that, again, now I'm not looking for a max anymore. I'm looking for a 0. So whenever the 0's over here, that's basically what I'm going to be looking for. So when I go back to this, I'm going to have to make an adjustment a quick one here to my expression, because now instead of being plus 3 here at the end, it's minus 5. So we'll notice that kind of shortened up my graph a little bit, but I'm looking for this 0 right here. So I'm like, okay, looking for a 0. So again, I'm trying to trap my 0 in. Left is up above. Hit my enter. Right just means it's going to be down below my axis, because again, I'm trapping it in. Get my enter. Go back towards there. And I find out it's going to be about... I'm going to have about a little under 2.5 seconds to figure this out. So we're going from my friend hitting the ball to me seeing it go up, to me seeing it coming down, and then me hitting it. That's my reaction time that I have. So it's not very long to think about this. So, even one more question. So suppose you hit the smash when the ball is 8 feet above the court. Okay. It takes 1/10 of a second for the ball you smash to hit the court on your friend's side of the net. I hope they have quick reflexes. What was the ball's initial vertical velocity coming off your racket? Oh dear. Okay, so this is a new one for us. We're still going to keep working with that same value. The 0 is still going to be working over here, because again, we're trying to find this initial velocity. Except now, I'm given a time. So when I look back at this, I go, okay, my starting point is 8 feet above the court. So I'm making a new equation now. So now my initial starting point's at 8. I actually have the t this time. So negative 16 t squared, the 0.1, the 1/10, plus 45t, which I know is 1/10. Now, here's the question though. You're looking at it and you're going, wait a minute. Harty, they're not giving me the velocity, I'm finding it. Well, heck, that's why I'm not supposed to use pen on this. I filled in too much information, because now there'd be nothing left to solve. Silly man, if I'm looking for the velocity, I gotta leave that open. So, we're going to clear that out. Quick drawing. You can see how fast my hand goes back and forth. Okay, so I'm looking for that initial velocity that's going to be occurring. So this time we're going algebra. Now I may not know off the top of my head what some of these other values equal. So if you need to punch those into the calculator to find them out, that's okay. So let me get that out of there. So negative 16 times 1/10 squared. Okay. So now that's what I'm looking at. Now I'm going, okay, if I'm trying to solve for v sub 0, I can combine my like terms here. So that would be $7.84 once I combine those. And you're like, oh, so I'm just solving. So I'm going to subtract the 7.84 to the other side. And then we're going to get into something that might blow our minds initially, but we will make it through okay. When I get to here, you're like, well, wait a minute. If I divide that by 1/10, I get a negative number. Yes. And that's okay. Yes. Because when you're looking for this initial velocity, initial vertical velocity coming off my racket, think about it for a minute. We're not going upward like we have been with all the rest of these. If you're smashing a tennis ball, you're coming basically down at a really sharp angle. That's where the negative's coming from. So that's what we're watching for with our velocity on this particular one. But that's pretty quick, 78 feet per second. I don't think I can react that fast. Probably get hit in the face with a tennis ball. But that's where my adjustment comes in on these. So sometimes I may be finding the velocity, sometimes I may be finding the time, sometimes I may be finding the height. It just depends on what's being asked for. So one more large one here to take a peek at, and then we'll kind of halt here and see how things are going, and hopefully have this set up where you're feeling a little bit comfy with this. All right, last one. Basketball player. Passing the ball to a teammate who catches it 11 feet above the court, just above the rim, and slam dunks it through the hoop. The first player, the initial player, releases the ball 5 feet above the court. Okay, there's my initial height. With an initial velocity of 21 feet per second. Okay, 21t. As usual, no big deal with my negative 16. You're like, well, what about the 11? That's where it's going to end up. So I'm going to end up at a higher point than I started at. As usual, I got to move the 11 out of there. How long is the ball in the air before being caught, assuming it's caught as it rises? All right, we need to find us, for our last part here, clear this out. When I go to graph this, so I'm looking at this and I'm going, okay, how long is the ball in the air before being caught? I need to find my 0. Oh, look how far down this is. Need to adjust our window here a little. You're like, wow, that's not very long. No, it's not, because I can't even really see that. Let's adjust one more time. Let's narrow this down a little bit. So when I go to find my 0, which may be a little bit more fun this time, you're like, whew. Again, I might need to use the y value a little bit more this time. Left, I'm going to be under. Right, I'm going to be over, and I am, whew, that's not much time. A little less than a second here. So now, I've just come to a brilliant theory. Tomorrow, what I am going to have you do is just spend your time playing with this. There is going to be a key here because I want you to be able to check your answers as you go.